The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Okay, so we're starting in on the last unit, and so we're going to be talking about kinetics for the rest of the semester. The last class is a bit of a review of everything we've done, but this is the last topic, and it's mostly in chapter 13, but there's a little bit in chapter 17. So if you notice on your problem set, the VSEPR is covered, which is in chapter 3, transition metals in chapter 16, kinetics in chapter 13, and some nuclear chemistry in chapter 17. So you're jumping back and forth between several different chapters in this last part of the course. So rates of chemical reactions and rate laws. So today's an introductory lecture to rates, and we'll introduce you to a lot of terms that you need to know. All right, so chemical reactions. So in addition to asking whether the reaction is likely to go as it is written, which is a thermodynamic question, we also want to know how fast that reaction will go. So kinetics is rates of reaction, that's what it is. And a kinetic experiment measures the rate at which a concentration of a substance taking place in the chemical reaction changes with time. So you're talking about changes in concentration with changes in time. So let's take a look at a chemical reaction. So this is the oxidation of glucose. Glucose and oxygen going to carbon dioxide and water. So as Professor Sayre told you in the first part of the course, this is the reason why we eat. We need glucose for energy. This is what drives our bodies. This is how we make ATP, which is our source of energy in our bodies. So this is the reason why we eat. Oxygen is the reason why we, what? Breathe. CO2 is the reason why we, and water is the reason why we, yes. So you know this reaction quite well. Really important reaction. So Professor Sayre told you about the thermodynamics of this reaction. She talked about delta G naught. And delta G naught equals what? Delta H minus T delta S. And so you can consider sort of how much, what you get out of this reaction, how spontaneous, how favorable it is, considering delta G, which depends on the value of delta H and the delta S, and of course also what temperature the reaction is. So in this case, delta H is a large negative number. So what type of reaction is that? Exothermic. Delta S naught is positive. So that's very favorable. You always want to increase entropy. And so delta G is a very large negative number. So this is a thermodynamically very favorable reaction. So if that's true, if you have glucose around, one might expect that when the glucose is sitting in air, in oxygen, that it would be forming CO2 and water. This is a really favorable reaction. So I brought some glucose with me today to class. So in here, these are some Hershey's Kisses. There's chocolate and there's sugar. So this is all sealed up away from oxygen. But according to this thermodynamics, if I open this up, this is a really favorable reaction. Air will enter the bag, and CO2 should come out. So I'm gonna open this up, and we'll see what happens. Of course, if you did this on your own, safety glasses might be a good idea. All right, I don't really see much happening. All right, well, let's observe this reaction over time. So what I want you to do, the TAs are going to hand this out, and during the course of the lecture, I want you to carefully study your Hershey's Kiss, and let me know at the end if you observe any CO2 coming off of this. And we'll watch one up here at some point. So Christine has one up here, which we can take a look at. All right, so you can help me with this experiment during the course of the class. Okay, so this brings up a point. It's thermodynamically favorable, yet we are not observing the reaction happening. So why is that? Well, it's favorable, but it's slow. So it's not only a measure. Thermodynamics are very important, but that's not the whole story. Rate, or kinetics, is also a very important part of what determines whether you're going to be observing this reaction happening. So, as these are being handed out, let's just consider these two terms for a moment. So this is going back to what Professor Sayre talked about, and these are actually right out of one of her handouts. So she told you about things that are stable or unstable. So if you're talking about stable, unstable, you're talking about delta G. You're talking about thermodynamics, the thermodynamic tendency to decompose. But that's not the whole story. You also have to consider whether it's labile or non-labile, also referred to as inert, and that refers to the rate. And so that's kinetics. So the reaction that we talked about, it might be that glucose is unstable. Thermodynamically, it wants to decompose, but it's also fairly non-labile. The rate at which it happens is very slow. So I think that most likely at the end, we've done this experiment before in class, no one has observed any CO2, but somehow the chocolate by the end of the class seems to have gone away. So, but yet there's no evidence of the water that's formed. So it's a little bit confusing. But in any case, these are important terms to know. So rate is important. And just as another example in terms of rate being important, someone might say to you that you could make $5 million. Again, rate is important. Will you make that $5 million in the next year, or would you have to live to an age of 1,562 to make that $5 million? So rate at which things are happening is very important. So in this case, this reaction can't be, has to go to some degree, because this is how we make energy to live. So this is really slow, but your body is using this reaction to get energy. So how does that happen? Well, it happens because there are enzymes. So in the body, it must be fast enough. So the body uses catalysts, enzymes, proteins that catalyze the reaction. They speed up the reaction, and that is what allows this reaction to work as their source of energy. So we will consider catalysts and enzymes a little later in this unit, but that's an important point. So let's talk about some of the factors affecting rates of reaction. So move over here. What are some factors that would affect how fast a reaction would go? Temperature. Someone say heat or temperature. What else might affect rates? Concentration. What about the one that was just up on that slide of how the oxidation of glucose works on the body? Use of catalysts. Okay, a couple other things. Nature of material. And mechanism, which we're going to be talking about. So in the next few lectures, we're going to be considering concentrations, nature of material, mechanisms, and toward the end, we're going to talk about temperature and catalysts. So that's where we're going in this unit, and how they all affect rates of reactions. So first, we have to introduce you to some terms and talk about measuring the rates of reaction. So here we have a reaction of NO2 gas, CO, carbon monoxide, NO gas, and CO2, carbon dioxide, which we just mentioned before in the last example. Suppose you're measuring a rate of this particular reaction. So you could, for example, plot the change in concentration of NO gas versus time. You're forming NO as the reaction goes. You're considering the rate of the reaction. You're looking at how much you form in a certain amount of time. So here might be what the data would look like. As time goes on, you see an increase, and then it starts to level off. You can consider the average rate, which would be defined as some change in concentration over a particular change in time. You could express that as the change or delta of the concentration of NO over the change in time, delta time. And you could pick some places and calculate an average rate. So you could draw lines over two different concentrations at two different times and calculate what the rate is in that interval. So we can do that, average rate, two different concentrations at those two different times, change in concentration over change in time, and that gives you a value. But this average rate then depends on the time interval chosen. So it's going to be a different rate here than it might have been down here or up here. So that tells you maybe something, but it doesn't necessarily tell you all the things that are going on because it just depends on a particular area. So instead of considering average rate, you can start talking about instantaneous rate, the rate at a particular time. And so that's instantaneous rate. And so you're really wanting to know what is the rate, say, at 150 seconds. At that particular moment in time, what was the rate? So here you're just talking about the limit as that change in time approaches 0. And that can also be expressed in terms of d, concentration of NO, dt. So the change in concentration of NO with time at a particular moment. So as that change in time approaches 0, the rate becomes the same as the slope of the line tangent to that particular point in time at time t, the one you're interested in. And so say we'll find this instantaneous rate at 150 seconds here. So we can do that, the rate at that particular time. So we're going to draw a line tangent to the curve and figure out the slope of that line. So we can do that, find the slope, get some different points, and look at the instantaneous rate. So we can calculate the slope of that line here and come up with a rate. So in this case, 7.7 times 10 to the minus 5, and this is in molar per second, which is a common unit for a rate. Okay, so that tells us about a particular instantaneous rate at one given time. And an important thing to consider is initial rate, and so that's the instantaneous rate at time equals 0. So the initial rate of the reaction. So that's a little bit about measuring rates, and we'll talk more about plotting data when you're trying to get out rate constants and other factors. So rate expressions. So we can express the rate of the reaction when we're measuring a reaction you can often pick to measure the increase in the amount of products being formed. You can also consider the decrease in the amount of reactants. So you can measure rate either way, looking for disappearance or looking for appearance. And often decisions about how you're going to measure the rate depends on how easy it is to measure a change in something. So there's usually practical considerations that go on here. So then the rate can be expressed in terms of the disappearance of one of the reactants, here NO2. So the rate is going to depend on how fast that's disappearing, or the disappearance of the second reactant over here, and the appearance then of one of the products or the other product. And this, of course, is only true if we assume there's no intermediates, because sometimes the rate at which a reactant will disappear will not be the same as the rate at which it'll appear, because there's lots of steps involved in between. So this comes back to mechanism, which we're going to talk about in next week. So, but this is what's known as the rate expressions. So let's look at an example. So here you have a reaction, 2HI gas going to H2 gas plus I2 gas. So the rate could be considered in terms of the disappearance of the reactant. And here we see that for every 2 HI that disappears, that's decomposed, we have 1 H2 and 1 I2. So if we're going to set up our rate expression, we're going to have to multiply this term by a half if it's going to be equal to the rate at which H2 appears or the rate at which I2 appears. So the stoichiometry here matters. So if you just looked at the rate of disappearance of HI, it wouldn't be equal to how fast that's forming, because 2 are going away for every one of each of these that is formed. So then in general, you would write the expression this way. So minus 1 over A, where A is the stoichiometry of reactant A, dA dt, minus 1 over B, dB dt, plus 1 over C, dC dt, plus 1 over D, dd dt. That's hard to say. All right, so those are rate expressions. Now we come to rate laws. So a rate law is the relationship between rates and concentrations. And those are going to be related by a proportionality constant called little k, rate constant. So big K was what? Equilibrium constant, and now we have little k, which is the rate constant. So a rate law is going to tell you how the rate depends on the things in the reactions. There'll be a rate constant, and there's going to be concentration terms, and it has to be experimentally determined what that rate law is, unless it's an elementary reaction, and we'll come to that in a few minutes. So suppose you have this particular reaction going. Your rate law would have some expression that looks like this. It'd have rate equals the rate constant, little k, times some concentrations. And here we're raised to the m and to the n, and those are known as the order of the reaction. And so m is the order of the reaction in A, and n is the order of the reaction in B. And little k, of course, is the rate constant. So how do you know what terms to put in there? And how do you know what the order of the reaction is? Well, these are experimentally determined. So the rate law is an experimental result, and you just can't look at the stoichiometry of the reaction and predict the rate law unless it's an elementary reaction. And so when you're designing mechanisms, you're creating steps and mechanisms that are elementary reactions, and then you can write the rate law based on the stoichiometry. And so you'll be told this is an elementary reaction, and then, that's fine. That'll be a step in a reaction. But otherwise, unless you know it's an elementary reaction, you can't just assume the stoichiometry is going to work. And there'll be experimental evidence to indicate the order of the reaction. Rate laws are not just limited to reactants. Sometimes product terms will appear. So you might see term for C or for D, the products of the reactions. And the order of the reactions can be integers, fractions, negative, or positive. Again, the order would be experimentally determined unless it's an elementary reaction. So let's look at various orders of reactions and consider how you would write the rate law, and also how you would figure out what was going on with the rate law. And the way the experiments are done is if you say double the concentration of something and then look at the effect of the rate. That's how you're going to figure out experimentally the order of the reaction. What effect it has if you keep everything else constant, double one thing, what happens to the rate. Then try doubling the next thing, keeping everything constant. And you would come up with the order of the reaction. So most of this is blank. There's a couple things written in your handout, but most of it's blank. So let's fill it all in. So we'll start up here with m equals 1, which is called first order. So for something that's first order, the rate would be K, the rate constant, times the concentration of A. And so M is the order of the reaction in A. So that would be your rate law. And so you can put a little 1 there if you want, but it's implied. All right, so that's the rate law. Now let's think about if you double the concentration of A with this rate law, what would happen to the rate of the reaction? It would double. All right, so let's look at second order then. So m equals 2, second order. So this would be written rate constant K times the concentration of A squared to the second order. So m equals 2. Now if you double the concentration, what happens to the rate? Quadruples. If you triple the concentration, what happens to the rate? So you had 9 times. So these are the kinds of problems that you'll get. Someone will give you in a problem set or in a test or in real life sometimes a whole bunch of data. It will talk about doubling or tripling concentrations, and then there's the effect on the rate. That's how the rate changed. Then you can figure out the order of the reaction. So let's go down here now. M equals minus 1. I don't think this has a name. I don't know what the name is if it does have one. But we can write the rate law for it. So the rate equals rate constant times the concentration of A to the minus 1. So M up here is minus 1. So let's think about what happens if we double the concentration in this case. What would happen to the rate? So you would half the rate. So it can also be a fraction. So you can have m equals minus a half, and that's shown here. So you would write that as K times the concentration of A raised to minus 1/2. So if you double the concentration of A in this case, what would happen to the rate? So it would be 0.7 times 2 raised to the minus 1/2. So some of these get a little complicated in seeing the patterns when you're analyzing the data. Some are more straightforward than others. But the ones where it's a negative and a fraction are a little more complicated to observe what pattern is happening. So going up here, we have m equals a half, and that's called half order. So the positive ones here have names. And so that then would be k times a raised to a half. And if we double the concentration here, what happens to the rate? So 1.4 times the rate. What do you think m equals 0 is called? Zero order. And what would the rate law be for this one? Yep, rate equals k. So what would happen if I double the concentration of A? Nothing. No effect on rate. So you can look for this in a list of examples where they're changing the concentration of A, and you can look at the effect. And if there's no effect on rate, then it's zero order. And so the term does not appear in the rate law. So there's some exercises on problem 10 on this. It's common. It's a good question for a final exam to think about looking at data and coming up with what the rate law for that expression is, for that particular reaction based on data. So you think about what's happening, what they're doing, and then what the effective rate is, and you can back calculate then what the order of the reaction had to be. So the next thing about rate laws is that the overall order of the reaction is simply the sum of the exponents. So the sum of all the individual orders. So if your rate law was your rate constant, and it's A to the 2, so that's what order in A? Second order. And what order in B? First order. And your overall order is going to be 3. So it will be overall third order, second order in A, first order in B, and overall third. So it always breaks my heart on a test when people get this part right, and they say, what's the overall order of the reaction? And they can't add the 1 and the 2 to get 3. So remember that part. That's like the give me points on an exam to be able to add these very small numbers and come up with the sum. So remember how to do that for me. So overall, it's just the sum of the individual orders. Okay, so here's the bad news, and that is the units for the rate constant K vary. So the units are going to have to do with what units you have for concentration and rates and what terms are in there. So there's no one unit that you can memorize and always know that that's what it's going to be. So you have to actually think about what the units for the rate constant are. So that's a little bit trickier. This one, much easier, just add. But the units are a little more complicated here. All right, so that's all you need to know about rate laws. So it's not too much. All right, so here are some of the problems with these kinds of experiments. So some of the data that you might get that you're trying to analyze may not be too perfect. Usually if it's in the textbook, it's pretty perfect data. But in general, these things can be tricky to do. And they can be tricky to get this good data to figure out what the order of the reactions are, because you're often measuring really small changes in concentration of material over brief intervals of time. So that can be technically challenging to do. And so the approach that's used then is to use these integrated rate laws. And so here you can express concentrations directly as a function of time. And this makes it easier to get at the information that you want. So let's look at a first order reaction. So you know what first order means now. So we just have one thing going to another thing in this particular example. Your first order for A Rate of a reaction could be written, the rate expression can be written in terms of the disappearance of A over time. And you know it's first order. You're told it's first order. So you can also write the rate law. So the rate law for first order reaction in A would just be the rate constant times the concentration of A. So M is 1 here. So now we can derive the first order integrated rate law from this simple expression right here. So what we're going to do is we're going to take the concentration terms and put them on one side of the expression, and we're going to take time terms and put them on the other side. So we're going to bring the concentration of A here over to this side of the expression. So there it is, 1 over the concentration of A. We have dt as well. And so we've moved that. And we've moved K and the negative sign over here. And we've moved the change in time over to the other side. So we have all the concentration terms on one side. We have rate terms and time terms on the other side. And now we can integrate. And we want to consider the change from the initial concentration of A to the O for original or to the 0. So the original amount that you have of A to the concentration of A you have at time t. And so we have our concentration expression. And in terms of time, we're looking from 0 time to time t. And now we can take this and solve this expression. So this is the same one. I'm just moving it up to the top of the screen. And so now we can express this in terms of natural log. So the natural log of the concentration of A at time t minus the natural log of the original concentration of A equals minus kt. And we can reorder that and put a box around it, which means it's going to be important later on. So we can rearrange this in terms of the natural log of the concentration A of time t minus kt plus the natural log of the initial concentration of A. And so we'll come back to this in a few minutes. We can also keep going and rearrange this in other ways. So we can rewrite this term instead of by subtracting them, rewrite it as this division. So natural log of the concentration of A at time t over the original concentration equals minus kt. And then we can take the inverse natural log. And so then on the other side, we have e raised to the minus kt. And we can write this in this expression, again, box. This is the way that you often see the first order integrated rate law, where you're solving for the concentration of A. Time t is equal to the original concentration of A times e to the minus kt. So how the concentration of A changes depends on the rate constant and the time that has elapsed. So this is often the way that the integrated first order rate law is written. Sometimes you may see a little bit different expressions, but usually this is the final expression that you see. And this is an equation for a straight line. And that's why it was boxed, because it's how data is going to be plotted. So if you're going to use that now and plot data, you can plot data that you collect. So the concentration of A as it's changing. So you're measuring how the concentration of A is changing versus time. And so here's your equation. The natural log of the concentration at time t equals minus kt plus the natural log of the original concentration of A. So you can see that this is the equation for this line. And so the intercept over here is going to tell you about the initial concentration of A And what you really want, the great thing that you want, are to determine rate constants for a particular reaction. So how do I get the rate constant out of this plot? From the slope, right? So the slope is going to be equal to minus k here. So we can solve then, if we plot our data that we measure over time, how it's changing after this amount of time, we have this much more, and we can plot the data, and we can pull out a rate constant. So this is a very useful way to get information about our particular reaction that we're interested in. So when you're talking about first order equations, reactions, you also often talk about half-lives. So the amount of time it takes for half of the material to react. So half-life is the time it takes for the original material to be reduced by a half. And its expression is in terms of t to the half, shown here. So let's derive an expression for the half-life of a first-order reaction. So we can take from above, from the integrated first-order rate laws, this expression, natural log of the concentration of A at a particular time over the concentration of the original material equals minus T, minus KT. The rate constant times time. All right, so for a first order half-life, we're talking about half of the material going away. So then we can go in and substitute in half of the original material being gone and solve for that. So we can take this. So the A at time t at a particular time, in this case, half of it is gone, so we can substitute in the original material divided by 2, because what we're interested in is the first half-life, so half of that original material is gone, so the time at time t2 that we're interested in, and now we've put t to the half, so it's not just at any time, but at a particular time at this particular condition for first order half-life. And then we can rearrange this expression here. And so this just becomes the natural log of a half. So the original concentrations will cancel out in this expression, and you're left with 1 over 2. Now we can solve for this, the number value. And so you get minus 0.6931. And then we want to rearrange this expression to solve for the half-life. So if we bring that over, we have half-life equals 0.6931 over k. So the one thing you'll notice in this expression, there's no term for A anymore. So half-life does not depend on the concentration. It depends on what instead? On K, on the rate constant, and rate constant depends on the material in question. So half-life depends on K, and K depends on material. So we talked about nature of material affecting rate. So here's one example. Some materials have much longer half-lives than other materials. So just to think about this question then. For the same material, how long does it take? Does it take longer for 1 ton to go to a half ton, or for 1 gram to go to a half gram? It's the same, right? So it's hard to think about this, but sometimes it seems like that should be wrong, but it doesn't. All right, so one last thing before you go. So let's just look at plots. This takes the same amount of time. So let's consider what it would look like if we plotted then concentration versus time for something that was first order. And so you would have a first half-life. You'd be at half the concentration of the material. The second half-life, after it had gone through another half-life, you'd be down to a quarter, and a third half-life, you're down to 0.125, and so that would give rise to a curve like this. So you have this kind of decay curve, and you can see where we're going on this. So on Monday, we're going to be talking about examples of half-life first-order reactions, which are nuclear decay reactions. So we'll talk a little about radioactivity, and that's where Chapter 17 comes in.